Okay, in this video I am going to talk about how we can construct the total characters corresponding to a reducible representation which stands for the transformation of bond vectors in a molecule. Did you understand anything? I will explain. What are the meanings of these terms, what I already said. For example, I have a molecule CH4. CH4 is a tetrahedral molecule like this one, right? CH4. So this is a tetrahedral molecule like this. Okay, and I have four bonds here, a central atom which is attached to four hydrogen atoms. So there are four bonds. Okay, and let me take each bond from the central atom to the other atom, okay, as a vector. So this is a vector like this. Okay, so this one is also a vector, this one is another vector, and this one is another vector. Okay, the direction of the vector is from central atom to the atom in the surface. Okay, so that these are called the bond vectors. Bond vectors. And there are four bond vectors in this molecule. Let me call this as R1, R2, R3, and R4. Okay, these are the bond vectors. And you can consider another molecule now, that is BF3. BF3, that's a planar molecule. Okay, BF3. BF3. This is BF3. Okay. Here also we have a central atom, that is boron, and boron is attached to three fluorine atoms. And here also we have the bond vectors, three bond vectors. These are the three bond vectors here. This is one bond vector, this is another bond vector, and this is another bond vectors. Okay, and so now you understand what is meant by a bond vector. And I am going to talk about what happens to these bond vectors when a molecule is subjected to symmetry operation in a point group that it belongs to. For example, CH4, this molecule belongs to the TD point group, right? Whereas BF3, that is a planar molecule, and this belongs to a D3H point group. D3H point group, right? Because it has a C3 axis, then 3C2, so it is a D3. Then it has a horizontal plane also, so it belongs to D3H point group. So we already know what are the elements present in the TD and the D3H, right? In TD we have the elements like E, then uh, C3. Okay, there are actually 8 C3 in the TD point group. 8 C3, then 3 C2, okay, and then 6 S4, okay, and the last one is 6 sigma D. So we have E, C3, C2, S4, and sigma D here as operations, and here in D3H we have E, then we have 2C3, okay, then we have a 3C2, okay, and then we have sigma H, then we have 2S3, and then we have a 3 sigma V. Okay, so these are the elements present in D3H. What we are going to do is we are going to perform each of these operations for these molecules, and then we will see how these bond vectors will transform when we are performing these operations. For example, when we are performing the E operation, nothing will happen to the bond vectors. The bond vectors will retain its position, right? But this is not the case when we are performing other operations, and that we will see in detail, and then we will make the matrices corresponding to these each transformation. Okay, so our basis set here in the TD point group, our basis set is R1, R2, R3, and R4. Okay, and we will see what happens to this. R1, R2, R3, and R4 when we are performing these operations. Okay, So this is belonging to TD point group. So it is a tetrahedral molecule. In order to show you what happens in a what happens during the symmetry operations in a tetrahedral molecule, let me put that tetrahedral molecule inside a cube. Okay, that is the best way to understand the symmetry operations in the tetrahedral molecule. Let me make a cube here. Okay. So here is a cube. Okay, and we construct this like this. So I have a cube here, and how we can place a tetrahedral molecule inside a cube? The central atom will be in the midpoint of the cube here. Okay, in the midpoint of the cube, the central atom will be there. Here, the central atom will be there, and the other four atoms. For example, in the case of CH4, the other four atoms means hydrogen atoms. In this particular case, will come in the alternate corners of the cube. For example, one of the hydrogen atoms will come here. This is one hydrogen atom here. Okay, this is one hydrogen atom, and this is another hydrogen atom. It will be in the alternate corner. So here comes one, and then here only and the other one can come. Okay, other one here, and the next one can come here only. Okay, so these are the four hydrogen atoms, and therefore the bond vectors will be like this. I will show you the bond vectors in these cases. So from the central atom to one hydrogen, one bond vector, then from the central atom to here, then from central atom to here, okay, and from the central atom to here also, here also. So these are the bond vectors, right? And now we can understand what is happening in this tetrahedral molecule during every operation. Let me call this one as R1. Okay, this one as R1. This is R1, and then let me call this one as R2. This is R2. Then this is R3, and this is R4. Okay, so these are the bond vectors. And now I am going to perform each operation. For example, I will perform E, then I will perform C3, then I will perform C2, S4, and the sigma D. Okay, and we will see how these bond vectors will transform. So during E, you know that actually nothing is happening in the molecule in the E operation, right? So during E operation, during this E operation, R1 is transformed as R1 itself. So in every case, I will say that R1, R2, and R3, R1, R2, R3, and R4. These are the bond vectors. So this is represented by a matrix, and this matrix is transformed into another matrix, that is R1 prime, R2 prime, R3 prime, and R4 prime. Okay, so these are the transformations. Okay, and we will see um, um, how these are affected. Okay, and we can see that during E nothing happens. Therefore, we can say that R1 is equal to R1 prime, R2 is equal to R2 prime. Okay, R3 is equal to R3 is equal to R3 prime, and R4 is equal to R4 prime. It means that nothing happens during during the E operation. Okay. Therefore, in matrix form, we can represent it like this. These four equations, four set of equations, this set of equations can be represented in a matrix form like this. Okay, that is 1 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. Okay, then R1, R1, R2, R3, R4. Here our basis set is R1, R2, R3, R4. Okay, the bond vectors. That is equal to R1 dash, R2 dash, R3 dash and R4 dash. Okay, so the transformation is like this. Here you can see that this equation means 1 into R1, that is R1 is equal to R1 dash. Then 1 into R2, that is R2 is equal to R2 dash. R3 is equal to R3 dash and so on. Okay, so these equations can be represented by this matrix like this. Okay, therefore the matrix corresponding to E, is equal to 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. This is the matrix corresponding to E. Now we can look in the matrix corresponding to C3. Okay, the next operation is C3. So how we can perform C3 operation in a tetrahedral molecule? C3 operation. C3 operation can be carried out about any bond vector. Okay, means we can rotate this cube in an axis passing through any bond vector. Okay, so you can take this bond vector R1 as the axis of the rotation, C3 rotation. Then what will happen when this cube is rotated about R1? R1 about ആയിട്ട് നമ്മൾ റൊട്ടേറ്റ് ചെയ്യുന്നു എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ എന്താ സംഭവിക്കുന്നത്? ഈ മോളിക്യൂൾസിൻ്റെ ഇതിനകത്തുള്ള R3 എന്ന് പറയുന്നത് R2ൻ്റെ പൊസിഷനിൽ പോകുന്നു, R2 R4ൻ്റെ പൊസിഷൻ പോകുന്നു, R4 R3യുടെയും പൊസിഷൻ പോകുന്നു. ഓക്കെ, സോ ഹിയർ ഐ ആം റൊട്ടേറ്റിംഗ് ദിസ് മോളിക്യൂൾ about R1. Okay, so the molecule's rotation here is like this, okay, about R1. So molecule is rotated like this, and when it is rotated, R1 goes in place of R2 goes in place of R4, R4 goes in place of R3, and R3 goes in place of R2. Okay, here I am doing this rotation. So during the C3 rotation, during C3 rotation, what will happen? R1 retains its position because the rotation is about R1, right? R1 retains its position because rotation is about R1. So R1 is equal to R1 dash. Okay, R1 retains its position. But what about R2? R2 in this case, R2 is going to the position of R2, R4, right? R2 is going to the position of R4. Therefore, we can write R2 dash is equal to R4, right? R2 dash is equal to R4. That is the new position of the R2 vector is R4. R2 is going in the place of R4. Therefore, the new position of the new state of R2 is nothing but R4. Therefore, we can write R4 is equal to R2 dash. R4 is equal to R2 dash. And what happens to R3? What happens to R3 in this rotation? R3 and R2 goes here, then R3 goes here, right? R3 goes here. Then R3 becomes, means R3 goes here, okay? R3 becomes R2, right? So the new position of R3 is R2, okay? Or we can say R2 is equal to new position of R3 is equal to R2. Therefore, we can say R2 is equal to R3 dash. New position of R3 is R3 dash, and that is R2. So R2 is equal to R3 dash. Okay, and what happens to R4? What happens to R4? R4 goes in place of R3. So R4 comes here, and therefore we can say that the new position of R4, that is R4 dash, is R3. Okay, R4 dash is equal to R3. So we can write R3 is equal to R4 dash. So in the matrix form, how can we write this in the matrix form? The matrix form, we can write it like this. Okay, let us construct a matrix. R1 is equal to R1 dash. Therefore, we can write 1 here, 1, 0, 0, 0. And R4 is equal to R2 dash. So we have to write 0, 0, 0, 1. Okay, and R3 dash is equal to R2. So we have to write 0, 1, 0, 0. And R4 dash is equal to R3. Therefore, we have to write 0, 0, 1, 0. Now you have to write R1, okay, R1, R2, R3, and R4. That is equal to R1 dash, R1 dash, R2 dash, R3 dash, and R4 dash. Okay, so these are the equations. So this equation states that R1 is equal to R1 dash, then R4 is equal to R4, because this element will be multiplied by this element. R4 is equal to R2 dash, like that. Okay, so the matrix corresponding to C3, the matrix corresponding to C3 now, C3 is equal to 1, 0, 0, 0, 0, 0, 0, 0, 0, 1. Okay, then 0, 1, 0, 0, and 0, 0, 1, 0. Okay, that is the matrix corresponding to R3, C3. Okay, now we can construct the matrix corresponding to C2. Okay, matrix corresponding to C2. Now C2 axis is the axis bisecting any two bonds, right? So let us consider a bond, an axis bisecting the R1 and R2, R1 and bond between, the bond angle between R1 and R2. Okay, so this is R1 and this is R2. There is an angle between R1 and R2. This is the tetrahedral angle, 109 degree 28 minutes. So there is an axis which is bisecting this R1 and R2. So that axis will pass through here, because this pass through the center of this space. So this is that C2 axis. Okay, and then it will pass through the midpoint of the molecule. Then it will then pass to the center of this down face, and then it will go like this. Okay, so that is the C2 axis. We have to consider only one C2 axis. And we can see what happens during this C2 operation. Okay, and during the C2 operation, what will happen? C2 means 180 degree rotation. This corner will rotate about this axis, and this corner will come here, right? And during 180 degree rotation, this corner will come here also, and this corner will go here. So what is happening actually during the C2 operation? R1 is exchanged with R2, and R3 is exchanged with R4. That is what is happening during the C2 operation. R1 is exchanging with R2, R3 is exchanging with R4. Therefore, we can write like R1 dash, that is the new position of R1. New position of R1. Where is the new position of R1? Where is R1 going? R1 is going to R2. Okay, that is R2. So the new vector corresponding to R1 after the C2 operation is R2. Okay, so like we can write like R1 dash is equal to R2. R2 is equal to R1 dash. What about R2 dash? So R2 dash is equal to R1, because R1 and R2 are exchanging their positions. So we can write R1 is equal to R2 dash. Write that like that. R3 dash is equal to R4, and R4 dash is equal to R3, because R4 and R3 are exchanging their positions. So how can we write the matrix corresponding to this? Okay, we can write the matrix. Now I think I don't need to write the complete matrix equation for you to understand how these are, how we can get the matrix. Maybe for this one also I can write the complete matrix equation, but for the next two operations I will skip this step. Okay, and I will write the matrix directly. Okay, here in this case we can write like matrix. Okay, R2 is equal to R1 dash. Okay, so we have to write 1 in the second place because it is R2 which is becoming equal to R1 dash. So 0, 1, 0, 0. Then next is R2 dash. So R1 becomes R2 dash. So 1 here, 0, 0, 0. Then R4 is equal to R3 dash. So 0, 0, 0, 1 and 0, 0, 1, 0. Okay, into into R1, R2, R3, R4 is equal to R1 dash, R1 dash, R2 dash, R3 dash and R4 dash. Okay. So this is the matrix equation corresponding to these four equations. So from this one we can say that the matrix corresponding to C2, matrix corresponding to C2 is matrix corresponding to C2 is 0 1 0 0 1 0 0 0 0 0 0 1 then 0 0 1 0. Okay, that is the matrix corresponding to C2. Now we can construct the matrix corresponding to S4. Okay, we don't need, we have other C2s also here, but I am not going for other C2s. Like that, we had 4 C3s here. I am not constructing the matrix for other C3s, right? This is just because the character corresponding to one C3 will be the character of the character corresponding to other C3 matrices also. Okay, you already know that. That is why I am not going to construct the characters for other operations. Okay, so now let me construct that for the next operation is next operation after C2 is S4. Okay, so S4 in this case, what is S4 in this case? S4 actually coincide with C2. Okay, the axis for C2 and axis for S4 operation both are same axis. Okay, so, but there are different operations. In the case of C2, there is a 180-degree rotation, that is the operation. But in the case of S4, it is a 90-degree rotation followed by a reflection. Therefore, even if the axis of C2 and S4 are same, the operations are completely different. Okay, I would never think that C2 and S4 are same because they share the same axis. That is not the case. The operations are different. So S4 in this case, how the S4 operations will happen in this molecule S4. So I already said that S4 and the C2 have the same axis. So we can consider the same axis what is considered here itself. That is the axis which is bisecting the angle between R1 and R2. That is the S4 axis also. Okay, but S4 axis is a 90-degree rotation. Therefore, what will happen during the 90-degree rotation? We are rotating this one, and during the 90-degree rotation, see the R1 will come here. R1 will come here. See, R1 will rotate 90 degree. Therefore, this corner of the cube will come here. So this will be the new position of R1 after 90-degree rotation. And then there will be a reflection perpendicular to the axis of rotation. So what will be the plane of that reflection? This is the plane of the reflection. See, there is a perpendicular plane like this, and about this plane we are reflecting it. So when this one is reflected, this R1 is reflected about this perpendicular plane, the reflection of R1 will come here, right? So during the entire operation, R1 which was here will come here. So R1 will go in place of actually R4. So R1 goes in place of R4. That is what is happening in the S4 rotation. R1 will go in place of R4. So let me write it like this here. R1 will go in place of R4. And what will happen to this R2? So R2 will come here, okay, during the rotation. Okay, this is like a clockwise rotation about this one. It is rotating like this. Okay, R2 will come here and then it is reflected here. So reflected, after reflection it will come in place of R3. So R2 will go in place of R3. R2 will go in place of R3. And what will happen to R3 and R4? R3 after rotation will go in this corner. Okay, after the clockwise rotation, it will go in this corner, and after the reflection, it will go in here. So R3 will go in place of R1. R3 will go in place of R1. R3 will go in place of R1, and R4 will go in place of R4 will go in place of R2. Okay, so these are the changes happening during the S4. So I can write it like equations like this. So R1 dash, okay, R1 dash is equal to that is R1 dash is new position of R1. So the new position of R1 is R4. We can write it like R4 is equal to R1 dash. Okay, and R2 dash is equal to R3. So R3 is equal to R2 dash. And new position of R3 is R1. Okay, therefore R3 dash is equal to R1, and R4 dash new position of R4, that is equal to R2. So these are the equations here. So corresponding to these, what is a matrix? Let me construct the matrix corresponding to S4. S4 matrix. S4 is equal to R1 dash, that will come from R1. So we can write like 0, 0, 0, 1. Okay. R2 dash, that will come from R3. So we can write 0, 0, 1, 0. And R3 dash will come from R1. So we can write 1, 0, 0, 0. And R4 dash will come from R2. So 0, 1, 0, 0. So that is a matrix corresponding to S4. Matrix corresponding to S4. Okay. So here I am considering the clockwise rotation. Okay. So here, and now if you are considering the anti-clockwise rotation, the things can change. Okay, that you have to keep in mind. So anyway, that is not problem. It is not going to affect our total character. So we can write it like this. And now, if I am going to consider sigma d, what is sigma d? That is the plane which is going in between the two bonds. Okay, the plane which is going in between the two bonds. So that sigma d plane will consist of two bonds, and also it will bisect the angle between two bonds. So you can consider R1, R2, the plane passing through R1 and R2. That is a sigma d plane. This plane, the plane passing through R1 and R2. So this plane. Okay. So this plane will be like this. So this corner and this corner. Okay. Corner. Then this corner and this corner. Okay. So this is the plane. So that is the plane we are considering now. This is the plane we are considering. So after reflection about this plane, what will happen? What will happen after reflection about this plane? R1 and R2 are already in this plane. Therefore, they will not change their positions. But R3 and R4 are the opposite sides of the plane. Therefore, R3 and R4 will exchange their positions. Okay. So we can write this in the matrix form. Okay. R1 and R2 will remain position. R3 and R4 will exchange their position. Therefore, the changes happening here are R1 dash during the sigma d. During the sigma d operation, R1 dash is equal to R1 itself, because R1 is not changing its position, and R2 dash is equal to R2 itself. But R3 dash is equal to R4 because they are exchanging their position, and R4 dash is equal to R3. So in the matrix form, we can write sigma d is equal to 1, 0, 0, 0, then R2 dash is equal to R2 itself. So 0, 1, 0, 0, and R3 dash is equal to R4. So we can write 0, 0, 0, 1, and R4 dash is equal to R3. So we can write 0, 0, 1, 0. Okay. That is the matrix corresponding to sigma d. Now we have all the matrices corresponding to different classes E, C3, C2, S4, and sigma d. So let me check the total character corresponding to this. Total character corresponding to this. Here in this case of E, the total character that is the sum of the characters along the diagonal, right? So this is equal to 4. And in the case of C2, C3, the total character is 0 only, because only one appear in the diagonal elements. Okay, so the total character is 1. And in the case of C2, total character is 0, 0, 0, 0. Total character is 0. Okay, and the case of S4, the total character is 0 again. And in the case of sigma d, the total character is 1 plus 1, that is equal to 2. Okay, see what is the total character we have obtained here. Total character is equal to 4, that corresponds to E. So E, then C3, and C2, S4, and sigma d. So the total character corresponding to E is 4, and that corresponds to C3 is 1. C3 1. That is corresponding to C2. C2 is equal to 0, 0, and total character corresponding to S4. S4 is equal to 0. Okay, and total character corresponding to sigma d is equal to 2. So the total character is 41002. 41002. Okay, so this is how we are making the total character corresponding to the bond transformations, bond vector transformations. So now you know how to construct it, but this is a very laborious process, a rigorous and laborious process, right? We have to make the metrics for every operation. We have to see what is happening in every operation, where R1 is going, where R3 is going. This type of things we have to consider lot of geometrical considerations. Then only we can construct all these matrices. You suppose that the molecule is even bigger. Okay, now we have a tetrahedral molecule. If you are going for octahedral molecule, there you have to consider 6 vectors, right? Then you have to construct the 6 by 6 matrices. So this is going to be again bigger, right? So it is not very easy to construct these total characters, but there are some easy ways to construct the total characters, and I will explain how you can construct the total character very easily. Okay, total character very easily corresponding to the bond transformation, bond vector transformation. Okay, you look at this E operation. In the case of E operation, what is happening? See, you can look which are the vectors retaining their positions. The vectors retaining their positions during the operation. Okay. In the case of E, all the vectors are retaining their position, right? All the vectors are retaining their position. Is R1 dash is equal to R1, R2 is equal to R2 dash is equal to R2. It means that all vectors are retaining their positions during E. So number of vectors retaining the position is equal to 4 here, and therefore the total character is also 4. Okay. Now you can look at C2 operation. In the case of C2 operation, how many vectors are retaining their position? R1 dash is equal to R1. So this is retaining the position. But here it is not retaining the position because R2 dash is equal to R4. So it is not retaining the position. And R2 is equal to R3 dash, not retaining the position. And R4 dash is equal to R3, that is also not retaining the position. Only one vector is retaining its position. You can just look at the geometry and see how it is happening. See, the C3 rotation is about the R1, right? This is the axis of the C3 rotation. Since R1 is the axis for the C3 rotation, R1 is not changing. All other vectors will change their position, right? It will make a 120-degree rotation about this C3 axis, and it will R2, R3 and R2, R3 and R4 will change their positions. So only one vector will retain their position during this operation. You can simply just look at the geometry of the molecule and say how many vectors are retaining the position. How we can say that? If the if the element, the symmetry element contains, if the symmetry element contains a particular vector, that vector will not change the position. All other vectors will change their position. In this case, the symmetry element is C3 and C3 contains R1. That is why R1 retain its position. All other vectors are out of this symmetry element. Therefore, they will exchange their positions, or they will change their position. So only one vector is retaining the position. That is why the total character here is 1. Okay. So you don't need to go for all these operations to find out the total character here. So because that is the only one coming in the diagonal position of the matrix. അല്ലേ ആ പൊസിഷൻ റീറ്റെയിൻ ചെയ്താൽ മാത്രമേ അത് ഡയഗണൽ പൊസിഷൻ വരുള്ളൂ. പൊസിഷൻ അത് മാറിക്കഴിഞ്ഞാൽ അത് വേറെ ഏതെങ്കിലും പൊസിഷൻ ഓഫ് ഡയഗണൽ എലമെന്റ്സ് ആയിരിക്കും, ഓഫ് ഡയഗണൽ എലമെന്റ്സ് ആയിട്ടോ അല്ലെങ്കിൽ മറ്റേതെങ്കിലും എലമെന്റ് ആയിട്ടോ ആയിരിക്കും മാറിപ്പോകുന്നത്. ഡയഗണൽ അല്ലാത്ത ഏതെങ്കിലും ഒരു എലമെന്റ് ആയിട്ടായിരിക്കും മാറിപ്പോകുന്നത്. ഓക്കെ. അപ്പം ഡയഗണൽ പൊസിഷൻ വരണമെന്നുണ്ടെങ്കിൽ അത് അതിന്റെ പൊസിഷൻ റീറ്റെയിൻ ചെയ്യണം. ദാറ്റ് ഈസ് വൈ ഇറ്റ് ഈസ് 1 ഹിയർ. And now what is happening during the C2? You can look at the geometry. C2 is the axis which is bisecting the R1 and R2. That will bisect R3 and R4 also. So none of the vectors are coming in the axis. Axis il orakta vector poli ivide varunilla. Therefore during the C2 operation all the vectors will change their positions. Vector position change cheyadirikkanamengil aa vector endu irikkanam axis thooടെ ആയിരിക്കണം പോയിരിക്കണം. But the C2 axis is not passing through any of the bonds. Therefore, all the vectors will change their position and therefore the total character will be 0. See, the total character here is 0. And now you can look for S4. S4 and C2 has the same axis. Therefore, you can see that all the vectors will change their position during S4 also, because S4 axis is not containing the C2. Not containing any vector. അതുകൊണ്ട് എന്ത് ചെയ്യും, S4 ആക്സിസിൽ കൂടിയുള്ള ഓപ്പറേഷൻ എന്ന് പറയുന്നത് എന്തായിരിക്കും, that is also not going to give any element in the diagonal position of the matrix, and therefore that matrix will also be 0. Okay. And here now sigma d. Sigma d is a plane which contains two vectors. Sigma d is a plane containing two vectors. In this case, we took the plane so that R1 and R2 are in the sigma d plane itself. Therefore, R1 and R2 will not change their position. Other two vectors will change their position. R3 and R4 was changing their position. Since two vectors were changing their position, the total character is 2. Therefore, you don't need to construct this entire matrix for getting the total character corresponding to the bond vector transformation. You can simply get the total character corresponding to the bond vector transformation just by looking into the geometry of the molecule and just by understanding which are the vectors falling in a particular symmetry element. Okay, like that you can see you can construct the total character corresponding to the transformation of bond vectors. So I hope you understood this one. And why this is very important, because we are going to use this total character corresponding to the transformation of bond vectors to assign the hybridization in a particular molecule. For example, we can assign the hybridization in the molecule that we already considered, CH4. Okay, you already know that it is sp3 hybridization. Carbon orbitals undergo sp3 hybridization. That is how the CH4 is formed. And then by group theory also you can predict that this belongs to the sp3 hybridization. In that procedure we will construct this total character. That is why I explained all these procedures here. Okay, this is very, very important in group theory to construct the total character corresponding to a reducible representation expressing the transformation of bond vectors. Okay. And I hope you understood this one. Now I will show you one more example. Then you will be short of how to construct the total character. Okay. For that I am going to take my second example. Okay. That is a trigonal planar molecule. That is BF3 in this particular example. That belong to the D3H. Okay. D3H. So how can we construct the total character corresponding to this molecule? the trigonal planar molecule in the D3H symmetry. Okay, the trigonal planar molecule belonging to the D3H symmetry. So let us construct the molecule like this. Okay, this is the molecule, and it has a C3 axis. You know that the C3 axis is passing through this central atom, and it will be perpendicular to this but the plane of the molecule. So this is a plane of the molecule. This is trigonal planar molecule, and this the point group is D3H. So the elements in the D3H point group are E, okay, then C3, okay, then C2, okay, then sigma H, then S3, and sigma V. Okay, these are the elements. Okay, so if you are taking the character table, you can see that it is E, then 2 C3 are there. Okay, because you can construct you can do C3 two times. Okay, so C3 and C3 square are there. That is why we write as 2 C3. Like that, we can write 3 C2, because 3 C2 axes are there in this molecule, and sigma H and 2 S3, okay, 2 S3 and 3 sigma V, okay, 3 sigma V. So these are the symmetry elements, and we will check what are the matrices corresponding to these symmetry elements. We don't need to construct the matrices. We can just simply assign the total character in this case. Okay, so I am going to assign the total character of the reducible representation corresponding to the bond transformation or bond vector transformation. So we have 3 bonds here, right? These are the 3 bonds. This is one bond, that is this one is one bond. Let me call this as R1. Okay, this is another bond, this is R2, and this is another bond, that is R3. Okay, so 3 bond vectors are there, R1, R2 and R3. And what will be the total character corresponding to? Total character corresponding to E. In the case of E, all the 3 vectors retains their position. Therefore, in the case of E, the total character will be 3. And what will be the total character corresponding to C3? C3 is the rotation about an angle, about an axis passing through the central atom, and at the same time perpendicular to the plane of the molecule. Okay, so the C3 will be passing through here, and if we are inserting an axis perpendicular to the plane of the board through this point, that will be the C3 axis. So during the C3 axis, R1 will go in place of R2, R2 will go in place of R3, and R3 will go in place of R1. If you are considering the clockwise rotation, if you are considering the anti-clockwise rotation, it will be R1 will go in place of R3, R3 will in place of R2, R2 in place of R1. It doesn't matter, because the total character is not going to change even if you are considering the clockwise rotation or anti-clockwise rotation. Okay, so the total character here is a 0, because all the vectors are changing their position during the C3. So total character is 0. And what about C2? C2 axis is any axis passing through one of these bonds. For example, if you are considering the axis, this one, this is a C3 axis, that is an axis passing through R3. Okay, so during this one, R1 and R2 will exchange their position during the C2, but R3 will retain its position. Okay, so during the C2 operation, only one bond vector will retain its position. Therefore, the total character corresponding to C2 is equal to 1. And what about the sigma H? Sigma H is the reflection corresponding to the horizontal plane. Horizontal plane is the plane perpendicular to the principal axis. Principal axis is C3, and the principal axis is perpendicular to the board of the plane. And therefore, the board of the plane in this case is the sigma H. That is the molecular plane itself. That is, sigma H contains R1, R2 and R3. All the bond vectors here are in the sigma H plane itself. Therefore, none of the bond vectors will change their position during the sigma H. Therefore, the total character here is 3. They will not change the position. And what about S3? S3 operation. And S3 actually coincides with the C3 here. S3 coincides with the C3. Means whatever C3 axis we considered, that is the S3 axis itself. The operations are different. C3 and S3 operations are different. C3 is just 120-degree rotation. S3 is not like that. We rotate it toward 120, then we make a reflection about the plane perpendicular to the axis of rotation. So S3 means this is R3 will come in place of R1. Then it is reflected about sigma h here. In this case, sigma h here. So the top hemisphere of every atom will go to the down, and the down hemisphere will come to the top. Therefore, this is a completely different operation. During the S3 or C3 operation, the top and the bottom hemisphere will not be exchanged. Okay, but during the S3 operation, the top and the bottom hemispheres of the atoms will be exchanged. So they are different operations. So anyway, during the S3, all the bond vectors will change their position. Therefore, S3 also will give 0. Okay, and what about sigma V? Sigma V is a vertical plane here. Means sigma V will go through any of the bonds. We can consider a plane perpendicular to the plane of the bond, and that plane is bisecting the bond angle between R1 and R2, and the plane is passing through R3. Okay, so during this reflection, R2 will go in place of R1, R1 will go in place of R2. Okay, and R3, since it is inside the plane, R3 will retain its position. So this is equal to 1. Okay, the total character corresponding to sigma V is equal to 1. See, now you constructed the total character of this molecule very easily without constructing the matrices itself. You just looked into the bond vectors and how the bond vectors are how the bond vectors are behaving during every operation, whether it is changing their position or whether it is retaining the position. Based on that, you have constructed the total character corresponding to a reducible representation for the transformation of the bond vectors. So these total characters are very important. See, now you can apply the reduction formula here. You can apply the reduction formula here, and you can see that this total character will be reduced to means the total character can be expressed as the sum of different symmetry species as present in each character, the character tables. Okay, so that I will explain while explaining the hybridization. That is not the matter of this discussion. Here, I just wanted to show you how to construct the total character corresponding to a reducible representation showing the transformation of bond vectors. Okay, and this is very important, and I have given you the tip how to construct this total character very easily even without constructing the matrices. Okay, and this we will apply, this knowledge we will apply now in assigning the hybridization of different molecules under different point groups. Okay, I hope you understood this lecture, and if you have any doubt, please don't hesitate to ask me. Okay, thank you for watching, and stay tuned.